So for problem 3 of test 1, we're considering 3 collinear points A, B, and C and a positive charge Q as shown in the diagram below. And point B lies within the thick wall of the metal container, whereas point C lies in the empty container in the interior. So what can we show so far that we know about this problem? So we know that inside the metal containers that the net electric field is going to be 0 because the charges cancel out. We also know that the inside of the empty container, which is surrounded by the metal container, is also going to have a net electric field of 0 due to the charges canceling out. So how do we find these charges? So the electric field, due to the charge Q, we're going to use our formula KQ over magnitude of R squared times R hat. And we know since the charge is positive that it's going in the plus x hat direction, as shown here, and that is for point A. And we can also see this because when we find R is positive as well, going from the observation location to the source. So that is pointing to the right, and then we also need to find the electric field due to the polarization of the metal. So to find the polarization of the metal, we have to look at the charge of Q, and since that is positive, we know that the left side of the metal container has to be negative and the right has to be positive. So moving from positive to negative, our E polarization is going to the right, and therefore the net electric field at location A is also going to the right. So it's not 0 here because these charges don't cancel out and they're both going to the right, and you can see that since the charges are summed, E net is greater than both of the individual charges. And then at point B, we're solving for the polarization of the metal as well, and that is going again from positive to negative. So this time it's going from to the left, since the polarization of the block is positive on the right and negative on the left. And then our electric field of Q would be the same. Since it's a further distance away, it would be smaller. And then again, since we're inside of the metal container, the net electric field would be 0. And the same goes for point C. So we have the polarization of the block from positive to negative going to in the negative x hat direction, and the electric field of Q going in the plus x hat direction. So that's how to solve the first part of that problem. And then for the second part, we are looking at points inside of an insulating plastic block rather than a metal. And this means that inside the block, our net electric field cannot be 0. So at point A, we have our electric field due to the charge positive Q pointing to the right, just as problem 1, and also the E the electric E polarization is also going to the right. So this part of the problem is going to be the same as 1 because we still have our polarization of the block where negative charges are on the left and positive charges are on the right, and we have dipoles inside the insulating plastic block going from negative to positive. And so at B, we need to show our induced dipole moment. And since dipoles go from negative to positive, it's going in the plus x hat direction from point B. And then at point C, it's also going from negative to positive, but you can see that the dipole moment is stronger on the left than the right, since it's closer to charge Q. But there are dipole moments inside of the block at all times. And then in the middle, this is showing the polarization. So it's in the opposite direction of the dipole moment, going from positive to negative. So that's in the negative x hat direction. And then again, we have our electric field due to the positive Q charge going in the plus x hat direction. And our E net is ultimately going in the plus x hat direction as well. So that's how to solve that problem. It's helpful to have the formulas and to check your work, and also remembering that the electric field for polarization is the opposite of the dipole moment, and dipole moments go from negative to positive, and the differences between an insulating plastic block or points lying inside an insulating plastic block and a metal container, that the insulating plastic block does not have a net electric charge of 0, and the metal container does. So yeah, that's how you solve this problem.